Here we discuss terminal velocity. Terminal velocity. With this heading, there was an English film. An action movie was there under this name Terminal Velocity. That film is also based on what we are going to see here in the practical sense. We consider that a lead shot which is falling through a viscous medium is slowing down because of Stokes force, or there exists a viscous drag with which the motion is restricted. Now we take the same situation here. There is an infinite column of viscous medium is there. In that, I am dropping a lead shot of definite radius r. Lead shot with a radius r. Radius r. And density rho. Rho is the density of the lead shot. And assume that sigma is the density of the liquid through which it is moving. Okay. Now, when I drop the lead shot here and observe the motion of that lead shot downward, you can see that the speed of the lead shot is going on increasing due to its weight. And if you observe that properly, you can find that after moving through a certain distance, the speed is going on increasing and increasing, and finally it attains a constant speed, after which the body is found to be moving with that same speed only, no further increase. This is possible for all the solid bodies which are moving through the viscous medium or falling through the viscous medium. After some time, it attains a constant steady speed. And that constant steady speed attained by the solid body is called terminal velocity. Definition: terminal velocity is defined as the constant velocity attained by a solid object when it is moving through a viscous medium. Now let us see how it is attaining the constant velocity. We found that the speed is gradually increasing and increasing and increasing, and the adjustment is coming based on, or the increase of that speed is now based on the weight of the body mg acting downward. This weight is making that body to move down. At the very same time, you can find that against this motion there will be two forces acting. One is up thrust. That is, as the body goes into the liquid medium, that medium is trying to expel that solid body. You call buoyancy force. The same is taken as up thrust. The force of the liquid upward on an object is called up thrust, buoyancy force. Along with that, there will be another force acting in the upward direction. That is our Stokes force. This is Stokes force. Stokes force. what are the forces coming on that moving body? One is its weight. Then against that upthrust, the buoyancy force, and the other one is Stokes force. Now, as you see, the body moves with a greater and greater speed through the viscous medium. Mg and the subthrust is not going to change. When the body is fully immersed, upthrust is constant only. Mg is there, that is also constant. But Stokes force, we studied that the force depends on the speed with which it is moving. Yes. So as you see, the speed is going on increasing. The Stokes force is gradually increasing, and after some time, the resultant force on this moving body becomes 0. Then it attains the terminal velocity. Now when the resultant force acting on the body is 0, force resultant force is 0, that means that acceleration is 0 for the body. Resultant acceleration is 0. If resultant acceleration is 0, means that velocity equal to a constant quantity. This is according to your second law of motion that you studied. So, resultant acceleration being 0, that doesn't mean that the body is always at rest. No. Now you understood that even though the resultant acceleration is 0, body will be moving but with a constant velocity. And this is the reason we define the Newton's first law as a body continue to be in a state of rest or of uniform motion unless an external force is applied on it. So, the rest and uniform motion are the same mechanical situations where the resultant force on the body is 0. So, now you understood that why it attains constant velocity, because the resultant force acting on it is 0. So, we can obtain an equation for this terminal velocity from this situation, that weight of the body minus upthrust plus Stokes force is equal to 0. Stokes force is the viscous drag. Then mg minus upthrust will be equal to Stokes force with the terminal velocity. Then I can write the equation as 4 by 3 pi r cube into rho, that is the mass of the solid body, into g, minus upthrust. We can define it as the weight of the liquid displaced by the body. This is according to Archimedes' principle. Okay, the buoyancy force is equal to the weight of the liquid displaced by the body. So when the solid sphere of radius r is immersed fully in this liquid, the volume of the liquid displaced will be equal to volume of the sphere. Then volume of the liquid displaced into density of the liquid gives mass of the liquid displaced into gravity gives the upthrust. That is equal to 6 pi eta r into v t. This t stands for terminal. So this velocity Vt is the terminal velocity. Only when that velocity is attained, the balancing is taking place. Now from this, we can cut short this as 4 by 3 pi r cube into rho minus sigma into g equal to 6 pi eta r into Vt. Now this is the balancing equation for attaining the terminal velocity of the motion of the body. Okay, so from this equation we can get equation for terminal velocity. Vt equal to, what do you get as Vt equal to Vt equal to, keeping this over there, r and 1 r from this goes, then pi and pi goes, therefore 2 by 9, then 6 comes over here, 16, 6 plus 6 into 3 is 18, so 2 by 9, pi and pi goes, so 2 by 9 into r square into rho minus sigma into g divided by, what is coming here? Eta. So 2 by 9 r square into rho minus sigma into g divided by eta, because r and 1 r from this goes, okay, pi and pi goes, 4 by 3, 3 by 9. Alright, so this is the equation for terminal velocity. So terminal velocity of the body is found to depend on what all things now? Terminal velocity directly proportional to square of the radius of that body. Then terminal velocity is inversely proportional to coefficient of viscosity of the viscous medium. Now the third one is that terminal velocity is directly proportional to the difference in the densities of the body and the viscous medium. Okay. Now this difference, let us discuss that one in detail. So let us consider the case. Suppose if I say Vt directly proportional to rho minus sigma, from the equation we got, if the density of the solid rho is greater than sigma, then Vt is positive. There is a condition coming. If rho minus sigma, rho is greater than sigma, Vt is positive. That means terminal velocity at that time when it goes down, or the body will be going down. But if density of the body is less than the density of the liquid, what happens? You know that the body will not go down. But in that case, if I forcefully take the body to the bottom of the liquid column and release from there, you can find that the body moves up gradually and attains a terminal velocity in the upward direction. And that there you get Vt equal to negative. Understood? So when you come to the calculations in this part, if you are coming across this condition and with the negative sign you are getting terminal velocity, that means that it can obtain terminal velocity in the upward motion through the viscous medium. Okay? And one more thing you can have here is the graph between the terminal velocity and the time of motion. Terminal velocity and the time of motion means if I take that graph, see this, this is velocity and this is time. Alright. You can find that when the starting point the velocity is 0, but as it drops down the velocity increases gradually, and that increase is found to be like this and reaches a constant speed after some time. And this particular speed is called the terminal velocity. So this is how the motion can be depicted with respect to time. So after this, this goes parallel with the time axis, because that point the velocity becomes a constant one. So these are the points relating to what we call terminal velocity. Okay.